I'm done, and I'm going to give you a sneak peek on our work about the semantics of shared memory in Intel CPU FPGA systems. So CPUs are great because they have a fixed set of instructions, making them easy to use. On the other hand, FPGAs have configurable logic that can be used for more specialized tasks. The FPGA only needs to power the circuitry that is needed to perform the computation of interest. Hence, all circuitry that is not needed is eliminated, meaning that a lot less power is utilized. Usually, designers must choose one or another depending on their application. But recently, systems that combine processors and programmable logic have started to become widespread. Programmers can nowadays spread their computation between a CPU and an FPGA such that both components run in parallel. Applications usually utilize the CPU to handle general computing, while the FPGA logic comes into play for more specialized custom tasks. Our aim is to answer fundamental questions about how to reason about programs that are split between the CPU and the FPGA. So we want to understand heterogeneous systems such as the Intel CPU FPGA one. Therefore, we want to see what kind of reorderings can affect the FPGA thread. Here we have the Intel Xeon plus Aria FPGA system. The FPGA is connected to the CPU via multiple channels. We will see that these channels can cause some very interesting behaviors that the programmer must take into account. So let's look at a simple example of coherency. Let's say that we send a write request to a certain address, then immediately issue a read request to the same address. We have no guarantee of receiving the new value. There are two ways to prevent this behavior. The first option is to use the same channel for the write request and the read request, but only issue the read request after we have received a response from the write request. And the second option is to use whatever channel we want, but also issue a fence between the two operations. So we have developed an axiomatic model and mechanized it in Alloy, and we have also developed a operational model and mechanized it in CBMC. We generated a large amount of traces to see if these two models matched, and afterwards we generated a large amount of litmus tests and we ran them on the hardware to see if our models are correct. We noticed in the literature that for some applications it is common for the CPU to communicate with the FPGA via a producer-consumer queue. Therefore, we have implemented such queues on the FPGA and on the CPU, and we have validated these queues using our memory model.